me, and I would like to thank also for organizing this event and for giving me the opportunity to speak. As already mentioned by Sergey, my topic that I would like to present today is charge regulation in charged systems, specifically in weak ampholytes. This is the work that we have done within the soft matter research group at Faculty of Science of Charles University in Prague. The main players of this game were Raju Lunkat, my PhD student who was doing the simulations, and Anastasia Murmiliuk, who was a PhD student of Mirek Stepanek. She is now a postdoc at neutron reactor in Garching in Munich, and she did most of the experimental work that I'm going to show today. To start with some motivation, quite often we hear about smart pH responsive polymer materials, and these are typically based on polyelectrolytes, either polyacids or polybases. When we talk about polyampholytes, we have in mind molecules that have both acidic and basic molecules or acidic and basic groups within the same molecule. And such polyampholytes can change charge from positive to negative in a rather broad pH range. So what one is typically interested in is a pH range in the whole experimentally accessible range between 0 and 14, as we can see on these two illustrations. Depending on the charge that the ampholyte acquires, it can interact with other charged objects or charged molecules in the solution that can change its physical properties. This is, of course, interesting for various applications such as drug delivery, cosmetics, food, or various kinds of sensing. However, it turns out that while the generic principles of this kind of charge-charge interaction are well known, the fine control of what is going on in these ampholytes is actually lacking. Why it is lacking, let me explain by first discussing the ionization of a weak acid, something that many of us know from the freshman university courses or maybe even from secondary school. We take an acidic group HA that dissociates into A- and releases a proton H+. We can define the degree of dissociation or the degree of ionization as the number of acid groups in the ionized form divided by the total number of acid groups present in the system. And we can characterize this acid-base ionization reaction by the equilibrium acidity constant, which in the ideal case can be defined as the product of concentrations of the species on the right-hand side divided by the concentration of the species of the left-hand side, multiplied by the reference concentration to make the whole object dimensionless. And we can rearrange that in such that we can express the acidity constant in terms of the ionization degree and concentration of H+ ions that can be related to the pH of the solution. Similarly to the pH, we can define the pKa of the weak acid, and combining that all together gives us the Henderson-Hasselbalch equation that relates the pH of the solution, pKa of the acid, and the ionization degree, yielding this kind of curve as we see on the right. The ionization degree as a function of the pH minus pK that is symmetric around the point where pH is equal to pK, and that corresponds to the ionization degree of 1/2 or roughly 50% of the acid groups being ionized. Now, if we try to take this concept further and try to apply this kind of equation to the ionization of a weak polyacid, as is depicted down here in the picture, we see that when such a polyacid, a polymeric molecule, gets ionized, this ionization brings a lot of charge to the chain, and these charges repel each other, thereby causing expansion of the chain as compared to its non-ionized state. These repulsions not only cause a conformational change, but they also affect the ionization response of the polymer, which is often described using the effective pK value that basically is obtained by taking the Henderson-Hasselbalch equation and turning it to a definition of the actual pK. However, this is only equal to the actual pK in the case of an ideal system. And obviously such a polymer with a lot of electrostatic interactions is not an ideal system. Therefore, there have been made various attempts in literature to describe that. One of the first ones is due to Kachalski and Gillis in 1949, who have shown that the pK effective can be expressed as the pKa plus the ionization degree times the electrostatic coupling, that is the key parameter, and an additional function that depends on the properties of the polymer. Well, while this is widely used, there is one problem with this description, and this is demonstrated in these figures, again, coming from a rather old paper from 1950s, plotting the effective pK as a function of ionization degree. We first noticed that this effective pK is not a constant. So if somebody asks me what is a pK effective of polyacrylic acid, I can show him this figure and say, well, you can choose anything between 4.5 and 8.0 is a good value, just depending on the conditions. For polymethacrylic acid, this is even worse because there is some kind of a plateau in between, indicating that the theory of Kachalski and Gillis actually fails to predict this curve because it would predict a straight line. So that tells us probably we need something more, and it brings me to the main research question of the work that I want to present today. What happens if we combine acids and bases within one molecule? Can we predict, oops, I think I've lost my slides somewhere in the middle, so never mind. Let us move this now further to the ionization of weak ampholytes. And that means we combine acids and bases within one molecule. And in our case, we decided to use peptides as suitable model ampholytes because they can be purchased at a predefined sequence. And we have a certain limited choice of natural amino acids with acidic and basic side chains, as is shown here, with various values of pKa, and here we see the corresponding solutions to the Henderson-Hasselbalch equation for these natural amino acids. The key parameter in constructing such an ampholyte then becomes what we call the delta pK, the difference between the pKa of the base and pKa of the acid. And as a proof of concept, we decided to examine that on two types of peptides. The first one consisting of a block of 5 glutamic acids and 5 histidines with the delta pK of plus 1.75. The other one consisting of 5 aspartic acids and 5 lysines with the delta pK of 6.88. So we have one small delta pK and one big delta pK. Let us have a look at an example of an ideal ampholyte, taking the lysine aspartic combination as an example. We have now two Henderson-Hasselbalch equations for the acid and base groups that differ in the argument of the logarithm. This difference in the argument of the logarithm translates to the different ionization curves. For the acid, it is non-ionized at low pH, its ionization increases as we increase the pH and then becomes fully ionized above the pKa. For the base, it is vice versa. It is fully ionized at a low pH, and as we increase the pH above the pKa of the base, then it loses its ionization. Then we can calculate the total charge on the peptide by simply taking the ionization degree of individual groups, multiplying by the number of these groups in the peptide and by their valency being -1 for the acids and +1 for the bases. In such an ideal model, we obtain this kind of a curve for the charge of peptide as a function of pH. And this curve does not depend on the interactions within the peptide, and it does not depend on the peptide sequence. Now it brings me to the research question that I wanted to mention before. The question is, can we predict the non-ideal ionization of ampholytes, at least as good as Kaczalski and Gillis could predict the ionization of some polyelectrolytes? That means definitely better than Henderson-Hasselbalch. The answer that I want to give you is yes, we can. We can do that using computer simulations and coarse-grained models. And in this point, it is really interesting to look in the literature because when we were preparing a review on simulations of weak polyelectrolytes in 2019, we found out that there are about 100 simulation studies of such systems. However, the number of those that were directly comparing with experiments, you could count on the fingers of one hand. And surprisingly, even though so few studies actually attempted the direct comparison, they all found very good agreement between such models. Therefore, it gives us a kind of good hope that we could be successful using the main assumption that the bare pKa of a polymer is the same as that of the free monomer or of the side chain of the corresponding amino acid in the case of the peptide. And it's the electrostatic interactions that are responsible for the shift of between the effective pK and the bare pK. The obvious question is, of course, we can always make predictions, but can such predictions be really quantitative? Before answering this question, let me tell you how we actually do that. We use so-called bead spring models of a polyelectrolyte, schematically depicted here, that contains the excluded volume interactions in terms of the steric repulsion and accounts for the chain connectivity. An important ingredient is the Coulomb interaction, accounting for charges on the chain, but not only that, also charges on the explicit ions in the solution, and all of that happens in an implicit solvent with a given dielectric permittivity corresponding to that of water. To this, we add the acid-base ionization reaction with the pK of the monomer as the input. And although this model looks really simple, I will try to convince you that it works well. What I need to mention is that this simulation is different from most simulations that you meet in the literature, because most simulations deal only with the evolution of configuration, which we do by molecular dynamics. What we add on top is the chemical reaction, accounting for the acid and base ionization, as is schematically shown here, where the HA groups turns to A- and H+ is released into the solution. The pH and the pK are our inputs, and they translate to the acceptance probability of the Monte Carlo procedure. That also includes the difference in the interaction energies. Thus, with pH and pK as the inputs, as the outputs, we obtain the equilibrium ionization states and the configurations of the system. Now, let me come back to the peptides. The two peptides that I have schematically, that I have introduced before, represented in a coarse-grained model of this kind, where the black beads here, denoted as C, represent the peptide backbone, and the red beads and blue beads represent the acidic and basic side chains. The parameters of this model, except for the pKa values, include also the distances between the side chains and the backbone, as well as within the backbone. Let me now show the simulation results for first of these peptides, the lysine aspartic with a delta pK of 6.88. And here we see that there is a clear deviation from the Henderson-Hasselbalch ideal titration curve. And we can understand this deviation by looking at the degree of ionization of acid and base groups separately. What we observe as a kind of non-intuitive observation is that even though the absolute value of the charge on the peptide is lower than that from the ideal titration curve, the ionization degrees of acid and base groups are actually higher than what one would expect from the ideal titration curve. And the resulting lower charge is just an effect of subtracting the partly ionized charge, the charge of the partly ionized acid group from the fully ionized base group on one side of the isoelectric point and doing the opposite on the other side of the isoelectric point. Now, if we look at the other peptide with a smaller delta pK of 1.75, then we see that there is no clear inflection points corresponding to the ionization of acid and base. And this is because these pK values are too close, and the change of the ionization degree of acid and base groups proceeds actually simultaneously in the same window of pH. In this case, again, we observe that the ionization of acid groups is higher than that of predicted by the Henderson-Hasselbalch. However, at the same time, we observe that the ionization degree of the base groups is lower than that predicted from the Henderson-Hasselbalch, altogether resulting again in the total charge in the absolute value being lower than that predicted for the ideal case. So we see here that the ionization of acid and base groups is mutually coupled, and that it is more or less symmetric around the isoelectric point. Now, these predictions are nice, but it's useful to know how reliable they are when they are really compared with the experiments. And because there were no experiments available, we decided to obtain them. First of them was the capillary zone electrophoresis, by which we could measure the electrophoretic mobility. That, however, yields only the effective charge as a function of pH, which is scaled by some unknown constant. To solve this problem, we calculate the charge of the pH by taking the mobility and normalizing by its maximum value at extreme pH values, when the peptide can be assumed to be fully charged. And we know that its charge should be either +5 or -5, depending on the pH. The other experiment that we could do is a potentiometric titration, where we add sodium hydroxide to the solution of peptide that was previously dissolved in hydrochloric acid. We measure the pH, we calculate the pOH, and then we know all the variables that we can substitute into the relation of electroneutrality to calculate the charge on the peptide as a function of pH. So we have two different methods to calculate the charge on the peptide as a function of pH, and we can compare them with the ideal Henderson-Hasselbalch equation and with the simulation results. As we see here, the general trend of the experiments is very well predicted by the simulations in both cases. However, there is a certain systematic deviation that we observe also in the difference of the isoelectric points between the ideal and the experimentally determined value. And we observe that the simulation actually yields a value of the isoelectric point that is close to the ideal. So this is the difference between the two vertical lines. However, there is one more experimental method, the nuclear magnetic resonance, that I didn't mention before, that allows us not only to determine the total charge on the peptide, it actually allows us to determine the degree of ionization of specific acid and base groups. As we see here, we look at the NMR spectrum of this carbon that is next to the carboxyl group, and you see how the position of the peak in the NMR spectrum travels with the changing pH. Using this, we can calculate the ionization degree from NMR data for acid and base groups separately. And these are the data points shown in these two curves. What we observe is that the trend produced or predicted by the simulation is very well represented by the NMR, except again for a systematic shift that is greatest for the aspartic acid that has the ionizable group closest to the peptide backbone. It is the smallest for the lysine that has the ionizable group pretty far from the backbone. And it is kind of intermediate for the other two, glutamic acid and histidine, that have the ionizable groups also at intermediate distance from the peptide backbone. So the assumption or the hypothesis that we made here is that actually we should not use the pK of the original amino acid, because upon incorporation into the peptide, its pK is shifted by replacing the substituents on the peptide backbone. And this has nothing to do with the electrostatic interaction along the peptide. To confirm that, we performed a new set of simulations with modified pK values, shifted by how much we observe the systematic shift. And we see that with these modified pK values, we can very nicely reproduce all NMR data. And indeed, we obtained also the correct isoelectric point. So let me play this for you again. These are the original pK values with shifted data comparing simulation and NMR, but showing the same trend. When we modify the inputs by changing the value a bit, we get almost a perfect match. That brings me to the interim conclusion, and I see that I'm a bit behind my time, so I'll try to be quick with the second part. From the first part, we've learned that the implicit solvent coarse grain models can quantitatively predict charge regulation in peptides, that the connectivity and geometry of the peptide play a crucial role in addition to the delta pK. The electrostatic interactions are the ones that dominate the deviations from the ideal behavior. And we have seen two different cases: delta pK greater than 0 or much greater than 0 when the acid and base groups ionize separately, and delta pK approximately 0 when the acid and base groups affect each other and change their ionization simultaneously. Finally, by comparing to the NMR, we have seen true shifts in this pK that were caused by the replacement of local substituent on the peptide backbone rather than by electrostatic interactions. Now I'll try to quickly guide you through the second part when we try to look at the role of delta pK and the sequence of the peptide, specifically examining the diblock sequence compared to the alternating sequence. Note here that in the diblock sequence, we have a block of acidic and a block of basic amino acids. In the alternating sequence, we always have the acid, base, acid, base, acid, base. When we look at the total charge on the peptide as a function of pH, comparing lysine and aspartic with a positive value of delta pK, and tyrosine and histidine, in the other case, with a negative value of delta pK, we observe more or less the same picture, very similar deviations from the Henderson-Hasselbalch between diblock and alternating sequence. And we see that we cannot really tell whether the delta pK is positive or negative. The shape of this curve looks qualitatively the same. We can only see that this delta pK is greater, seeing that the inflection points are further apart. So it suggests that it's actually the absolute value of delta pK that determines the inflection points and the dependence of charge on the pH. However, a completely different picture emerges if we look at the ionization of individual acid and base groups, because here we observe that with a positive delta pK at the isoelectric point, all acid and base groups are fully charged, and the zero net charge of the ampholyte is just caused by the cancellation of these two types of charges. On the other hand, with a negative delta pK, we see that at the isoelectric point, no groups on the ampholyte are charged, so the net zero charge on the ampholyte is caused by really no charge being present. Nevertheless, when we calculate the total charge as a function of pH, the curve looks very similar. Let me now examine the same case for the glutamic histidine combination, where the delta pK is close to zero. Here we see that if we compare the ionization of acid and base groups, there is a rather significant difference between the diblock and alternating sequence. However, we observe that the enhanced ionization of the acid group is more or less the same as the enhanced ionization of the base group, meaning that the ampholyte acquires an increased amount of positive and increased amount of negative charge, the net result being again a curve that looks almost the same for a diblock and alternating sequence. However, even though this suggests that the degree of ionization, that the sequence does not matter too much, this is not quite true if we look at the conformation of these peptides measured by the end-to-end distance and plot it as a function of difference mean pH minus Pi, where Pi is the isoelectric point. Here we see that depending on the type of the peptide and depending on the delta pK, we always observe a minimum in the end-to-end distance around the isoelectric point and a maximum at either highly positive or highly negative pH minus Pi, meaning low pH or high pH. We also see that the diblock sequence is affected much more than the alternating, which has a end-to-end distance that does not change with a pH too much. What happens to the conformation is best seen in the simulation snapshots, where I took much longer blocks of the lysines, 45 lysines and 45 aspartic acid. Here at pH 2, we observe that the blue guys, these are the lysines fully ionized at pH 2, are rather stretched, whereas the aspartic groups are non-ionized and they are coiled. The opposite picture we observe at pH 12. The red aspartic groups are fully ionized and the lysines are less ionized and somewhat coiled. And if we look at pH 7, we see that all groups are ionized, resulting in a compact conformation of the peptide that is actually caused by the attraction between oppositely charged groups compensating each other and forming this kind of a droplet-like structure. That brings me to the conclusions of part 2. We have observed that the delta pK determines which groups are ionized and what the curve of the total charge as a function of pH looks like. The sequence has little effect on the charge, but it affects the conformation. And we have seen that in many cases, we observe a cancellation of two competing effects. One of them is the repulsion between charges of the same sign, of the opposite, repulsion between the charges of the same sign. The other one is attraction between charges of the opposite signs. Last thing that I would like to say, where this work goes further, now we have understood, I believe, how to model charge regulation in ampholytes and especially in short, simple peptides. So what we would like to do is to predict this charge regulation in either flexible peptides or some synthetic polyampholytes synthesized in the group of Felix Schacher at the University of Vienna, or to achieve some kind of bottom-up design of peptides or ampholytes in general with specific pH-dependent properties. With this, I would like to thank you for your attention, and I will be happy to